That's alpha herpes viruses as they actually exist in vivo. So now let's talk about the immune response that controls them. The way to think, or the way I view host immunity to viral diseases is effectively the same as hurdles that a runner's jumping over. The first hurdle that any virus is going to encounter is going to be the physical and epithelial barriers of the skin. Okay? Most of the time, viruses don't get past these barriers. And when they don't get past these barriers, what happens is sort of a non-productive infection. We just don't even know what happens. Nobody ever goes to their doctor and says, you know, doc, I was exposed to an infectious virus that didn't get past my skin. Doesn't happen. Doctors always see the viruses, viral infections, that get really far along in this process. And they have to get past not only these innate immune barriers, but they have to get past 3 more barriers. And we'll talk about those last 3 barriers. The first is the innate immune response. Most viruses don't get past that. If they do get past that, that's when we start to engage the adaptive immune response. B cells making antibody and CD8 T cells actually going after virus-infected cells. So if we first look at how the interferon system works, it's pretty simple. Every cell in your body, when it's infected with a virus, has the ability to recognize that infection. There's a whole slew of different sensor mechanisms. There's no point in going into it. Let's just say that our cells have the innate ability to recognize viral infections within about 20 or 30 minutes. They notice some of the unusual patterns of nucleic acid synthesis or something, and they put up this interferon warning system. All it means is they're secreting 2 short-range hormones called cytokines, either interferon alpha or interferon beta. They're both basically 170 amino acid proteins. And every cell in your body has receptors for interferon alpha or interferon beta. So effectively, it's a virus-induced warning system. The bells and whistles go off, interferon secreted, and from the time this virus enters a cell and undergoes replication, it might take 12 or even 18 hours. The effects of interferon in neighboring cells only take about 3 or 4 hours. So interferon is always going to win the race. When this viral infection spreads to a cell already exposed to interferon, this cell is going to be way more resistant to viral infections. It's going to slow down the spread of the virus. And if T cells get involved, they can make, it's a different molecule, but it's got a similar activity. It's called interferon gamma. And these 2 cytokines can work together to really make cells super resistant to viral replication. Okay, so this is the interferon system. So the way we generally think of it working, a virus comes in and infects a cell. This cell, virus-infected cell, it's probably going to die. That's the most likely outcome. But it can warn all of its buddies in the neighborhood there's something wrong. This short-range hormone acts on all the adjacent cells, and it upregulates a whole suite for probably about 200 or 300 different proteins. I just offered 2 examples. Some of those proteins that exist or that are induced are things like MHC class 1, probably one of the most important molecules in allowing a virus-infected cell to talk to a CD8 T cell. Likewise, protein kinase R, something that directly interferes with the ability of a virus to translate its proteins. Okay, so basically the defense barriers go up to slow down viral infection. This happens in each and every time you're infected with a virus. And the way to illustrate this, if we look at some cells that have not been treated with interferon versus those that have been treated with interferon in a laboratory setting, what you'll see is something like this. In this well of untreated cells, you see an inoculum of about 200 or 300 infectious units of herpes simplex virus type 1, where each red dot is an infectious center started with 1 virus particle. The exact same inoculum of virus was applied to this culture over here that was pre-treated with interferon alpha. It's just harder for the virus to spread. It doesn't stop it from replicating altogether, but it slows it down a lot. And that's the role of interferon. So interferon is simply a virus-induced warning system. Here you see an eye that's been infected with a green fluorescent protein expressing strain of HSV1. And the reason the whole cornea of this mouse is not covered with green is because these cells out here have been hit with interferon released from the cells that were initially infected with the virus, and it's slowing down the spread of that virus. So this is a virus-induced warning system that renders cells adjacent to a site of virus replication more resistant or non-permissive before the infectious virions can reach those cells. That's the first hurdle. Second hurdle is antibodies. Antibodies add on top of that. So when B cells are activated by a viral protein and they differentiate into plasma cells and make antibody, if those antibodies bind to a virus-infected cell or an infectious virion, they can again slow down the spread of that virus. So one way we think of this is in terms of neutralizing antibodies. Normally, a virion, when it comes up to a cell, has to trick that cell into taking it in, and then it can start its replication cycle. If somebody has antibodies that coat those virions before they reach the cell, you stop the infection. It's a bit of an oversimplification, but it illustrates the point that antibodies basically work against viral infections. Okay, same point. Here's a herpes simplex virus virion being coated in antibodies. That's going to slow it down. As well as slowing it down, you're going to induce a pro-inflammatory response that draws white blood cells, such as T cells, to the site of viral infection. All right, so then the third layer, the white blood cells that we're drawing in. It's not the only antiviral white blood cell, but it's one of the ones we really focus on. CD8 positive T cells. What do? CD8 positive T cells actually interact directly with virus-infected cells via a molecule called MHC class 1, which again, I mentioned before, is what gets upregulated by 10 or 20-fold by interferon alpha. This virus-infected cell is grinding up peptides, viral proteins within it, putting them up on MHC class 1. And if you have a T cell that recognizes that viral peptide as foreign, it triggers this T cell to actively attack the virus-infected cell and kill it, or to secrete interferon gamma, which can work together with the interferon alpha and beta to suppress viral replication. What the T cell really sees to make all of this happen, if we look down on this, so if we look at this MHC class 1 and bring it over here, if we look down at the top of MHC class 1, immunologists often describe this as the hot dog and the bun. MHC class 1 is the bun. It is presenting a hot dog, a piece of virus, a viral peptide. In three-dimensional space, this is what it looks like. And this is what the T cell receptor looks at. It interacts with MHC class 1, and if it sees its special peptide that really makes it angry, it responds. Okay, so let's look a little bit at what cytotoxic T cells can do in terms of the attack. And we're going to go here to the immune response, and we're going to open this video on T cell killing. And I have to turn on the sound.
In this example, epithelial cells. Usurping their biosynthetic viruses are intracellular pathogens that infect cells of the body. In this example, epithelial cells. Usurping their biosynthetic machinery to produce new viral proteins. Degradation of virus proteins within the cell allows viral peptides to be displayed at the cell surface, bound to MHC class 1 molecules. CD8 T cells that recognize these MHC peptide complexes are activated and kill the infected cell. Having killed one cell, the T cell can move to a new target, kill that cell, and move on again. The killing process is initiated when the T cell receptor and CD8 together bind to an MHC class 1 molecule bearing a viral peptide, producing signals that activate the T cell. Cytotoxic T cells contain membrane vesicles called cytotoxic granules, which package the proteins that kill target cells. The most important of these are a protein called perforin and a set of proteases called granzymes. These proteins are complex with a scaffolding protein called surglycin. Activation of the T cell causes the release of the content of these vesicles, delivering the proteins directly onto the surface of the target cell. Although the exact mechanism is not known, the perforin facilitates the delivery of the granzymes into the cytosol. At this point, the target cell is destined for death, and the T cell can migrate onwards to find a new target cell. The process of cell death initiated by the granzymes uses the same basic cellular machinery that gives rise to apoptosis. The granzymes target various cellular proteins that regulate apoptosis, such as BID and procaspase 3.
All right, and we'll stop that there. The main point is that the reason CD8 positive T cells are such an efficient killing machine when it comes to controlling viral infection is because one CD8 positive T cell could potentially kill hundreds of virus infected cells before those cells can release their new infectious virions. All right, so that's the essence of immunity to viruses. That is a series of hurdles, and the last three that I told you about once we get beyond the epithelial barriers are the interferon system, antibodies, and finally T cells. So we come back to herpes simplex, a virus that I told you that despite our immune systems can reactivate from latency, thumb its nose at the immune system, and still reactivate, be asymptomatically shed, or cause recurrent disease. At the heart of how that happens is the fact that herpes simplex virus encodes countermeasures for each of these layers of the immune defenses.